What's up, guys? Welcome back to another LeetCode video walkthrough. Today we're going to be going over LeetCode number 297, serialize and deserialize a binary tree. So, serialization is a process of converting a data structure or object into a sequence of bits so that it can be stored in a file or memory buffer, or transmitted across a network connection link to be reconstructed later in the same or another computer environment. Design an algorithm to serialize and deserialize a binary tree. There's no restriction on how your serialization/deserialization algorithm should work, and you just need to ensure that a binary tree can be serialized to a string, and that this string can be deserialized to the original tree structure. So some clarification, the input-output format is the same as how LeetCode serializes a binary tree, and you do not necessarily need to follow this format, so please be creative in coming up with different approaches yourself. So some examples are as follows. If you're given this tree, and so the root is 1, left subtree is just a single node of 2, and then the right subtree is 3, and then 4, 5. Basically, you're given the root, and you have to output the same tree, except it has to go through the serialization and deserialization process. So a high-level walkthrough of this would be to first serialize into a string by using a recursive DFS algorithm, and how you would do this is by using the pre-order traversal to simply go through the node values in order of current, left, and then right. So for example, at any point in our recursion, if a node is none, we simply return append n to the list of values that we're building. Otherwise, we append the node's value and then run the same steps for the left and right trees. And in the end, we return the list, except what we do is we join it on the comma separator to return a string. And then we deserialize this string by using DFS to implement the same pre-order traversal that we did to serialize, except each time that we're doing it, what we're doing is creating a new tree node and instantiating the left and right pointers of the tree nodes to successive DFS calls. So how we would do this is we can create a variable I that tracks the index, and if the vals at I is equal to the character n, then what we do is we increment I and return none. Else, what we would do is create a tree node with the value of vals at index I, and increment I by 1 before setting the left pointer to a DFS call and the right pointer to another DFS call. And this is a sort of like a recursive backtracking algorithm. And so going over the example in more detail, let's say we have this tree. So initially we have an empty result array, and our DFS stack will be initialized to the very first node, which is 1. And what we do is we append this 1 to result, and we look at the left and right children. So first we look at the left child, which is 2, and we append this to result. And even though it has no children, technically they're both none, so we would also have to append 2's left child, which is basically none. And as we saw before, when this happens, we just have to append an n, and then because none has no children, it can be crossed off, and we move to 2's right child, which is also none. Once again, we append n, and for the same reason, we can cross off none here. And then because both of 2's children have been appended to result, we can cross 2 off. And that takes care of the left subtree. And now we can go to the right subtree, which starts with this node of 3. So add that to the stack, add it to result, and add both of 3's children. So first we go to the left child, which is 4, add it to result, and add both of 4's children to the DFS stack. And for the same reason, both of these are none, we can cross them off and then move on. And that takes care of 4. So now we go to 3's right child, which is 5. added to result, and it also has two non-children. So we end the result. Result with two ends. And now that we have this result array, what we simply do is we use the join operator on the comma. So what we get back is a string that looks like this: 1, 2, n, 3, 4, n, 5, n. And we can use this string to deserialize the tree. So going to our deserialization algorithm, as we said before, we have a variable I that tracks the index in this values list that we're iterating through. And starting at 0, we have 1. So we add 1 to the DFS stack. And as this is happening, I'm just going to draw the tree that's being built. So I'll just use this color. So we have 1, and we increment I by 1, and we call the same method on the left and right pointers. So the left pointer for 1 is going to be the next call, which goes to the value of 2, and we can add 2 here, and then we get to an n value, and that just indicates a none node. So now that 2's left value is taken care of, we go to the right value, and so that's also n, and that is again a none node. So all we do is increment I by 1. So I is 4, and then so basically this takes care of the left subtree, and now we're on the right subtree. So with I being 4, we get to 3, and then we make a new tree node with the value 3, and now increment I by 1 and go to the next node, which is not n, it's 4, and we add this to the left pointer because that comes first, and then then we're just gonna skip over these two values because they're both n. So just say n, and 4 is taken care of. We increment I by 2, so this becomes 6, this becomes 7, and now we're on 8. And now we're moving into the right subtree that starts at node 3. So what we do is do the same process. We have 5, it's not a non-null node, so what we do is create the tree node, and then for each of 5's children, which are both none, we would do the same process, and both these are taken care of, and eventually I increments to 11. So, and this is beyond the length of our list. So as you can see, we've serialized this tree into a list of values, and then deserialized this tree into this completely new object, and these are identical, and which proves that the algorithm works. And yep, that was just a basic pre-order traversal of a binary tree problem.